Okay, so today is lecture 11, February 2022, or February 16th, sorry, 2022. And today we'll finalize the encoding. And we do quiz 2. Okay, so let's again let me show this figure. Where is it? And honestly, I did not try it before. Let's try it. So this is the quantizer we are talking about, okay? So assume that for 0 and 1, Gaussian of 0 and 1, this was whatever 0.9, this is whatever 1.5, and so on. And this was so 0.9 minus 0.9, 0.45, 1.5, 0.45. This is 0.45, 1.5, right? We don't have this. Okay, so now we want to change the mean. So changing the mean, meaning shifting the whole, let's say n of 10, as you mentioned, and 1. So are clustered around 10, but your value is 1. So what we said that this is instead of 0.9, this will be 10.9, this will be whatever 11.5, and so on. So now what you are saying is that how what's the quantized level? So quantized level, yeah, I think it should be shifted. Yes. So both should be shifted. I did not try it before. Sorry for this. So yes, both x's and a's should be shifted. I did not give a shifting in the quiz. Yes, no. Maybe if I should have done, and I could have done answer this correctly first time. What do you mean? So now if you generate, Shabab, if you go to Matlab, Shabab, if you go to Matlab and generate numbers using a Gaussian of 0 mean and unit variance, the numbers most of the time, Shabab, most of the time will be 0.01, 0.05, 0.1, 0.7, whatever, minus 0.01, minus, it will be all around 1. But if you do it here, it will be 10.01, 10.05, yani roughly 10.1, 10.7. It will be clustered around 10. Okay. So either you do it this way, or you subtract the mean from the input signal and then use the same quantizer. Okay. So another way to do this is to subtract the mean from the input signal and then just use the quantizer as is. And then at the output you add the 10 again. Yes, because it will be a bigger quantizer. How it will look like? What's wrong? So this will be x-axis starts from 10. So for the y, you can have different scale على x وعلى y, right? So, yes. Yes, so this will be 10.45. This will be 10 minus 0.45, which is 9 point something. Yeah, انتوا يعني شباب in drawing the x and y axis, you can draw it for any center. It's common to use 0 and 0 as the center. If all of your signal resides somewhere else, you don't need to have the center as 0 and 0, but you have to mark it in your figure. Okay. Yes. It's always being assumed that it's not a signal that's being received. What do you mean? The quantizer only has distance between points. That's all we. Sure. Again, changing the mean will shift the quantizer left and right and up and down. Changing the variance will change the distances between the points. Stretching, like stretching. And if I have the same 0 and 10, if I have n of 0 and 10, what will happen? It's the same quantizer, but it's enlarged. يعني صار big one, okay? Whatever. So you, as if like you zoom in, so it's or zoom out, and it becomes like this. There's no shifting. The center is the same if the mean is the same. Okay. The points we are receiving are around the 10. So we shift the quantizer. We can shift them to around the 0. Yeah, so the same quantizer, instead of be centered at 0 and 0 and 0, to be at 10 and 10. So this, the center point is 10 and 10. So we always make the point we are receiving and the quantizer at the same. Yeah, if I have the input signal mean is not 0, that's what we will use. Okay. Yes. Y equals AX. بس نخلص. لو نغمة حلوة خلينا. Yes. If what? Y equals AX plus B. And in this case, we have to find A and B. If you want to shift and scale, yes. Depends. Yes. And like, I mean, if we get B, because we find A from the variance equation, and then after that we calculate for B. Shouldn't we shift by B only, not by A? Well, not by like shifting exactly. لا يعني assume انت you have both changes in the mean and the variance. That's what you are asking. Yeah, so you have AX plus B. A you're going to find from the equation of the variance because scaling doesn't. Yes. Then after that, scaling does change the variance. Scaling changes the variance. Shifting doesn't change the variance. Shifting does not change the variance. Yes. So you get A from the variance equation, and then you go back to the mean equation, which is going A expected of X plus B. You have A, and then you calculate for B. Shouldn't the shift be the same amount as B? Yes. B becomes exactly the mean. So yes. Right? Yes. So for this, the bigger one that we plot, we said no, for 10 and 1. 10 and 1. This will be 10 and 10, right? The center will be 10 and 10. Like what, because in terms here, what you're saying is what I have, if I have eta of مو 10 10, I'm doing different numbers عشان not confused. Whatever. 110. 110. So what do you do? Y equals variance of Y equals A squared variance. Yeah, بترجع 10 and 10. Let's do 25. So Y equals 5x plus 10. Right? So that the variance, sorry, no, it's the other way around. The other way around. So it's let's assume this is 10, 25. So Y equals 5x plus 10, right? So how do you do this? What will be the center? 10 and 10. And what will be the step? So the way to do this right, enlarge it and then shift it. Don't shift it and then enlarge it. Okay? Because if you shift it and then enlarge it, it will be something like 5x plus 10. Okay? So these are different. So you have to shift, you have to enlarge and then shift. Well, give me good ideas for the midterm. I was not planning to get into, and this is not a major part of the course. The core of the course starts next chapter. Yeah, these are just preliminary to the course. Anyhow, طيب. Yes. رأيي ناخذ الكويز ونمشي بلا محاضرة. شباب. Yes. What's that? For gray coding, what matters is that only adjacent levels they differ by. That's what matters. Because eventually, when you send this long stream of ones and zeros, it will not matter. If you have very long string, the probability of having 1 is 0.5, probability of having 0 is 0.5. So regardless of where you start, it's the same.
What is the systematic way to do it?
I don't know. I think there is a way. There is a way to do it. Yeah, and if I will ask you to do a gray code, it will be two bits or 3 bits. There is a way. Just change 1 bit at a time. Yeah, this is the natural binary coding. Yes. There should be a way. I don't know. There should be a way. But try to do it for change 1 bit at a time and see. Yeah, you have to throw it. There should be a way, صراحة. I don't know. There should be a way. طيب شباب. So let's continue with, we were doing BCM, which is pulse شباب code modulation. This all of your wasting time is taken from your quiz time. So it's better for you not to waste a lot of time. Okay. Let me just bring the PCM. Sorry for this. Okay. So what we did last time, this is our PCM system that we are considering. And we said this is the anti-aliasing filter. We sample, we quantize, we assign ones and zeros to each level, and then the whole thing, we call it the process of pulse code modulation. And we mentioned that non-uniform quantization is better than uniform. Why? Because we can use more levels in the regions with higher probability. This is the same thing that we also use non-uniform quantization to assign, like in speech signals, let's say, in speech signals, we also use non-uniform quantization speech signals to assign more levels to assign more levels to regions with low amplitudes, which are more common in speech signals. What's the advantage of this? This way, we can keep relatively the same signal to noise ratio. Why is that? Let's assume that the signal that we are quantizing will look something like this. So most of the time it's a small signal, but I have areas of large signal. So now if you use uniform levels, so assume that, let's do very, very stupid levels. Maybe I should not have done this. Sorry. Let's do it again. So I have something like this. As you can see, most of the signal will be quantized to this level or this level. I have, like, I can have also more levels. Those levels I will have, rarely the signal will be those levels. So a best way to do this is to do what? To have more levels in this region. Yani, put whatever, and I know my drawing is not the best. So smaller deltas, larger delta here. So now if you have smaller delta, then when you quantize the signal, the error will be small compared to the signal, right? So smaller delta, we mentioned before, that the quantization noise, assuming uniform quantization noise, is square over 12, right? And also, signal to noise ratio is what? So signal power على noise power اللي هي delta square over 12. So now, in general, if you use smaller delta, means the noise power is smaller, right? If you use larger delta, larger noise power. So if my signal is large, I can use large delta. If my signal is small, I can use smaller delta, so that the ratio more or less will be the same. You cannot keep it fixed, but you can at least try to keep a signal to noise ratio steady. And we'll see a figure to compare how to do this and then what's the resulting signal to noise ratio. But the idea itself is just as simple as this. Okay. So there are two standards. There are two standards to this, which are okay, the A law, what we call the A law, which is used in North America. It's used in telephone systems, in all حتى wireless systems, North America. And the mu law is used in North America. And the A law choose the rest of the world. طبعا نحن in this part we are only users, right? What's the mu law? So in practice, don't use larger delta and smaller delta. What you use something, a trick, a small trick. You come to the signal before you quantize it using equal deltas, you compress it. If it's large, you compress it. If it's small, you enlarge it, so that you introduce some harmony among the different parts of the signal, and you do the opposite, of course, at the receiver. Okay. So the mu law, we compress the signal according to the following equation. Which is y, the output signal equals what? Ln, sorry, 1 over ln 1 plus mu times ln 1 plus mu m over mp, where m is the input signal, mb is the input signal maximum. So that 0 less than m over. شوفي شباب في شيء؟ ان شاء الله مدير انت جايب كرسي خاص. سلامات. Where for the A law equation, and you find the equation in your book, I will just write it quickly. A over ln am over mp when 0 less than m over mp less than 1 over a, and 1 over 1 plus ln a times 1 plus ln a m over mp لما m over mp less than 1 over a less than equal to 1. So what's this input-output relationship looks like? Looks like this. Okay. These are the this is the input-output relationship using those, the mu law and the A law. So this is your normalized input signal. So the x-axis is the normalized input signal, and this is the output. So if mu equals 0, so ln 1 over ln 1, they cancel, the output is y is if mu equals 0, there should be an m there. For a equals 1, let's see, check for a. Then a equals 1. So for if mu equals 0, so this is ln, not log. Yeah, but it will be ln, and you have it on both, so you have to take the derivative to find the. It's not just divide by. Because if m equals 0, it will be ln 1 over ln 1. So the output is 1. Anyhow, the whole idea is something like this. A compressor will look something like this. This is input, and this is the output. If you have the relation between the input and the output, something like this. So if what does this process or this filter do to your input signal? If your signal is small, let's assume that this is the input signal. Okay, this is your input signal. What's your output signal? Let's do it here. So this is the, so here it's more or less like it. Of course, you have it on both sides. So however if this is whatever 10, this will be, so your output signal will be something like, you compress the large parts of the signal and you keep the small parts as is, or even if you have your relation was something like this, you can boost your smaller parts of the signal while keeping the larger parts as is. So the higher is the mu, the smaller parts, these are the smaller parts. See here, it's m over mp, so the maximum is 1. So this is the normalized signal. So when the signal itself is small, you are on this part. So if your current signal is 0.1, 0.1 equals m over mp. Assume whatever. Assume mp equals 10. Your maximum value of the signal is 10. So when m equals 1, what will be the output? If you are not using any mu equals 0, then the output is 0.1. When the signal is so m equals 1, said m equals, sorry, so m over mp equals 0.1, which means m over mp equals 0.1, which means m equals 1. When m over mp equals 0.5, which means m equals 5. If m equals 5, the output is what? Output is 0.5. What's wrong? This is input, this is the output. So if m itself, m was, we said, if m is 1, so 1 over 10 is 0.1. The output is 0.1. When the input is, we said 5, which means that 5 over 10 is 0.5. The output is 0.5. When the input is 10, then the output is yeah. So So this Celia, I want to show what's the effect of here. We are not scaling, right? So now if you use this one, so if this is formula, so here no compression. So now let's use m higher than 0. So for m equals 1, let's use another table here, whatever, m output. For mu equals 100, let's say. So when input is 1 over 10 is 0.1. The output is تقريبا 0.5. However, when m equals 5, which is 0.5, it's 0.7. This is mu, yes, mu. I'm using mu 100, yes. So 0.8. When it's 8, less than 0.9, 0.85 maybe, and so on. So the larger is your signal, the less is that. So you are compressing the larger part of the signal, and then you are using at the output you are using the same delta. Why are you doing this? So we do this to introduce. I'm not expanding. No. How do I? You are compressing the yeah, and you are introducing, depends. You are introducing compressing the larger part of the signal, and yes, probably introducing some help to the smaller part, so that eventually what you will get, I will write down. We do this to introduce some harmony to the signal levels, maybe boosting smaller parts and compressing larger parts to keep SNR steady. So if we look at the resulting SNR, I think in the book it has this is what you will get. Yeah, I will show where is it. 1 second, where is it? Where's my signal? So this is the SNR for if you use the mu compressor. So if mu equals 0, as you can see, as the signal power increases, signal to noise ratio keeps increasing, صح؟ عندك كل ما the larger is your signal, the larger is your signal to noise ratio. However, if you use this mu law, you get something like this. You keep a good steady for different parts of the signal. You have the same performance for the different parts of the signal. Especially, yani, this part is not that important. What's important is when the signal is very low. This is a very low signal to noise ratio. So you boost your signal at the low ranges, and you don't really harm the large ranges because you already have a good signal quality at the large ranges. Okay, a signal to noise ratio in this case, I think is for the mu law. Signal to noise ratio is 3 L squared على ln 1 plus mu squared. So this is roughly the resulting signal to noise ratio. So the system model that you are asking about, we use this is what we use in systems. Okay, I need to keep. So this is the non-uniform quantizer. What you have in here, so you remove your quantizer and you introduce this block in front of you instead of your quantizer. So you have your sampler, your anti-aliasing signal at the beginning, and then the input sample, you boost it or you reduce it according to this, and you do the opposite at the receiver. So this is the, usually this is called the compressor. It's the compressor, and this is the expander, and then jointly they are called combander. The compression and then expansion at the receiver. This way you can, and this is equivalent to using a non-uniform quantizer, but effectively you are using a uniform quantizer but with a modified signal. Okay.
For example, since the rest of the world is using the A law and then the US using the new law, someone calls someone.
Yeah, the telephone systems, I'm not going through that section. If you want to read it in the book, there is, because this is not the only difference. There are difference in how you group and how you multiplex signals at the subscribers. So there's an interface layer between the two systems whenever you want two systems to call each other, especially when we are talking about the landline. Now cellular systems is using the same standard. There's one entity to standardize 5G, 4G, with 5G. So خلاص, once they decide on, and up to 3G, we had two totally different systems with 3G. في كان LTE, one based on TDMA, one based on CDMA. CDMA was only in the US. But now, after 3G, we are having one system for standardization. There's an entity called 3GPP that I think they are at release, whatever now, 20. They decide on what technologies to adopt, what modulations to adopt, everything that's will be implemented in fifth generation. Fifth generation is still being standardized yet, because there are frequencies that haven't been used, haven't been introduced to the market yet. Okay. طيب. So now a smart person came and said, I have an idea which is called DPCM, which is differential pulse code modulation. Because this guy, he was thinking, the whole problem is when we have large range of the signal, right? I have strong signal and have a small signal. So he said, one way to solve this problem, let's not send the value of the sample itself. Instead of sending the sample itself, why don't we take the difference between each two samples? And since we are sampling with Nyquist rate or more than Nyquist rate, then samples are very close to each other. Then the value of the signal will not change a lot from sample to sample. So instead of sending the sample itself, let's send the difference. And we agree between the transmitter and the receiver that we'll start from a certain value, and then we build on it. So if you send the difference, it's the same as if you send the signal, right? Because if you know the reference point, the first point you add it to the reference point, and the second one you add, you keep adding. And the difference will have a smaller range, right? So instead of sending the sample, the quantized sample, let's say, the quantized sample itself, we send the difference between two samples. No, we quantize. We take the difference and then quantize. Okay? The range is very small. So what happens? So, what's the rationale for this? Signal level does not change much from sample to sample, from sample to sample, right? So lower dynamic range, right? Which means for the same number of levels, using the same number of levels, smaller delta can be used. Because the levels will be very small, very close to each other, which means less quantization error, right? Fine. So here, so we say you send, so send dk, which is mk minus mk minus 1, which is the difference. Yes.
How can we determine the shape of the receiver? We are only going to send the difference.
Because you said we start from a reference value. We agree from the transmitter and the receiver. The first value we'll send is 10. And then you'll send 0.1. So you know the next one was 10.1. Then there. So we have a certain reference. Okay? طيب. Then what happened? Even a smarter guy came. He said, we'll not send the difference. What we will do, I will predict the signal, the sample, the next sample. I have the samples coming. So before the next sample comes, I will predict its value, and then I will send the difference between the sample and its prediction. Because if you are estimating the sample, you will get closer even to the sample. So a smarter way to do this, of course, if your estimator is good, right? A smarter way to do this is to send dk, which is mk minus m hat k, where m hat is an estimate of mk based on previous samples. Yes.
Would the send and the receiver have the same meter?
Of course, yeah, these are protocols. So the transmitter and the receiver, they know they need to agree on what's going on. You cannot.
It is sent by the
Transmitter. Yes.
So the transmitter estimates the value based on what he already has, and then checks the actual value. Then send that. But the estimator,
The receiver will also do a predictor. Will do estimation. Yes. Yes.
So after he does the estimation, he adds the difference.
Yes. Yes. So how to do the estimation? Yes. So we said يعني احنا in a better way to do pulse code modulation, instead of sending the sample itself, we'll send the difference between two different samples, which will lower the range. Then I will have less error. I can use smaller deltas. طيب, a better way even to do this, instead of sending the difference between each two samples, until the samples are coming to you, okay? So you can use the samples to estimate the next sample before it comes. You can predict what will be the next sample based on the previous samples. We'll see how to do this, how to estimate it. And then you will send the difference between m of k and m hat of k. Question?
samples, you send the difference of the first.
شباب, don't worry about the transient periods. And all of this, and any transmission in communication, there's always preliminary bits and preliminary signals and pilots that they start, and then when there's a steady state, then they start to apply this. And don't worry about the transient parts of signal. There are frames and there are many measures that are put in place to make sure that we can implement this. Don't worry about the starting. So how do we do the estimation? We do the estimation, or the how to predict. I'll try to finish in 7 minutes or so. How to predict m hat of t. or m hat of k. Prediction will be based on the Taylor series expansion. Not sure, probably you are covering something like this in the DSP course, or you will do it later. But basically, Taylor series, what does it say? It says that the value of the signal, you are at MT, you want to predict the signal at T plus TS, where TS is the sampling time. So it's the next step. It's MT plus TS times M dot of T. So of course here we have to assume that the signal is differentiable, and then TS squared over 2 factorial M double T, and so on. This is the Taylor expansion. So assuming that TS is very small, we are doing Nyquist rate or more than Nyquist rate. So let's focus on the first two terms. Okay. Of course, if you can do it for all terms, you have the exact prediction. So let's focus on those and do this in discrete time. So let's T and TS, let's say K plus 1. So this will be MK plus TS. And then M dot. What's M dot of T? Let's see. So if this is my signal, and roughly, this is T, this is T minus TS, right? So M dot of T, derivative is what, basically? Is the slope, right? So if this is your whatever, it's the slope of this line. So if the slope of this line, what's the slope? The slope, I can estimate it as, this is the whatever, the tan of this signal, which is this over this. So this part, so this is time, this is T, this is M of T. Yes, so this is M of T, this is roughly M of T minus TS. Divided by, what's this? TS. So the derivative is basically, I can write it, so this equals M of K plus TS times M of K minus M of K minus 1 over TS. So this is basically 2 MK minus MK minus 1. So this is a very good estimator for the next sample. If you want to estimate MK plus 1, it's basically 2 times the current sample minus the previous sample. Of course, as I said, you can take this if you have access. Depends again in your transmitter how much memory you want to store the previous samples to use them to estimate. All of this because it takes power, it takes time, processing power. So in general, yes, 1 second. In general, the estimator is a weighted sum of the previous samples. So in general, you can write MK as A1 M of K minus 1 plus A2 M of K minus 2 plus A3 whatever M of K minus 3 and so on. And the estimator will look something like this. Okay, yes. It will look something like this. So it's a function of all the previous samples. You keep delaying the signals and then you multiply them by, depends on how many samples you want to use in your estimator. Question? Quick question, yes. Why is this one is better than the difference? Because you are estimating the signal. You get closer to the signal, right? You are usually the previous sample is a very simple estimator. You can use the previous sample. The previous sample is an estimator of the signal. You can look at the previous sample as a special case of this. You are just using the previous sample to estimate the signal. But this should give you a much better, because again, you are comparing two cases. I'm estimating the next sample by the current sample, or I'm estimating the next sample by 2 times this sample minus the one, even 2 steps before this sample. Based on the dynamics of the signal and the Taylor series, this should be much better. Yes? Can we use machine learning? It depends. Machine learning, you have to have, generally, I did not do machine learning, but you have to have a lot of data. And usually machine learning is very now in the millimeter wave with terahertz. If you want to do things real time and fast, and you need to do things really fast, you have a challenge with machine learning. Okay, so usually, and these kind of things, you don't need a very complicated estimator. Because your main idea is you want to reduce the dynamic range. So with this 2-step estimator, I think you will do a very good job. You especially if you're sampling, because probably will not be able to cover it. And you have one more thing to do here, which is what we call a delta encoder. Delta encoder is a special case of DPCM, which is you have very fast sample, at least 4 times the sampling rate. You sample very fast. So now its samples will be very close to each other. So what you will do 2 levels only. You will use 2 levels. If the sample is increasing, you send 1. If it's decreasing, you send 0. That's it. And at the receiver, you keep, again, having a reference, you keep adding and subtracting. And then you will have very, very good encoder. But the condition is you have to have very fast sampler. Forever, you keep, because the signal is changing. We will talk about delta. What's the size of the delta? Yes, it depends. There's also an adaptive delta, because if it's very small and the signal is moving fast, you will take time to track it. If it's large, sometimes you miss the details of the signal. So we'll talk about this probably beginning of next class. Okay, right. I will stop at this point, Shabab. And nobody's attending online, so I can stop recording.